Okay, welcome everyone. This lecture will be about well control in drilling operation. I don't know whether you guys have already had any course in drilling and well control or not, but anyhow, I'm going to start from scratch. So I will talk about well control in general, the importance of well control, uh, the kick indicators, how can we detect the kick, also the causes of kick, the equipment we have on a rig in case of we have kick, and well killing methods, mainly drillers and weight and weight. And at last, if we have time, I'll talk about volumetric method, which is not a well killing method, but it is used when we don't have the opportunity to fully circulate. So I'll start with the definition of well control. Basically, well control is the management of dangerous effects caused by the unexpected release of formation fluid. So when we are drilling, obviously this happens while drilling through permeable formation. Basically, well control is not an issue when we are drilling through an impermeable formation. When we are drilling through permeable formation and formation fluid starts entering the wellbore unwantedly and unexpectedly, we should be able to manage the situation in a safe manner way. This is basically called well control. It's absolutely crucial during drilling operation, and this obviously does not happen on a daily basis, and this is not wanted at all. However, because of the possible consequences of such an event, all the drilling engineers need to be fully aware of this of the topic. They have to have knowledge on how to deal with such an issue. That's why I always teach this as the first lecture in my drilling classes. Um as you can see, the reasons we need to know about that, first of all, is the risk. I mean, the lives of the personnel. Uh, if we don't know how to deal with the kick may end up being a blowout and it will cause severe damage. It may cost lives, it may cost the equipment, it may have environmental issues, especially if this happens in an offshore environment. Even if it does not become a blowout, it is still non-productive time. It's not desirable. So basically, we lose money. It makes the operation more expensive. For all these reasons, we need to know about well control. We need to know about kick, and we need to know about blowout. Um, there is a difference between a kick and blowout. Obviously, the kick is when formation fluid starts entering the wellbore, and we can have control over the situation, and we can manage the formation fluid which is entering the wellbore. However, if for any reason we lose the control over the operation and formation fluid reaches the surface in an uncontrolled manner, then this becomes a blowout. Obviously, blowout is much more costly and much more dangerous than kick. At the end of the lecture, let me let me say this. If you have any question, please go ahead and ask questions. Frankly, I hate monologues and I prefer dialogues. So if you have any question, go ahead and ask. If you have a question in your mind, I guarantee that probably 30% of the class are having the same question and they may not answer. They may not ask the question because of several reasons. Maybe they're shy, but don't be shy. Ask your questions. And if you don't understand any part of the lectures or any part of the talk, please stop me and ask me to explain it in a way that you understand. And the last one is the rig equipment. Obviously, if a blowout happens, then we may end up losing the rig and the well. So this is an infamous picture of what happened in Macondo in 2010. So you see the size of the calamity here. It was catastrophic, and if I'm not mistaken, BP had to pay $20 billion fine for the incident, and it was a well-controlled problem. So I think this picture is pretty self-explanatory. It tells us about the size of the damage in the Gulf of Mexico. One of the questions which may come to mind is, when kick happens, when formation fluid starts entering the wellbore, how much time do we have to prevent that from reaching the surface in an uncontrolled manner? Or on the other hand, on the other word, how much time we have to prevent a kick from becoming a kick, to become a blowout? So, is there any question? If there is any question, please go ahead and ask. I don't know the routine. I think Mayer is going to ask.
Dr. Hussein, the questions will be at the end of the lecture. So go ahead, finish your lecture, then the question will be at the end.
Okay. So this is the short video I always show on when I teach. And as you can see here, this is a tripping out operation, and the drilling crew is tripping out and see what is happening. So so far everything is normal. They're picking up the pipe, break out the pipe. But from this point forward, and you can see the time at the top of the so you can see the time here. Now, as you can see here, the drilling mud is coming out of the wellbore, which is not supposed to, because when we're tripping out during the tripping out operation, the well must be in static condition, meaning that no formation fluid entering the wellbore, nor drilling mud entering the formation. But here you see that drilling mud is coming out of the wellbore. Obviously, the reason is something is pushing out formation fluid out of the wellbore. And what we have inside the wellbore to push the drilling mud out of the wellbore is nothing but formation fluid. So obviously, formation fluid is entering the wellbore and the kick is happening. But as you can see here, the crew are not well prepared to cope with to deal with the condition. And the other thing I would like to draw your attention is, as the time passes, you see the situation gets worse. So, and I'll talk about the reason why, as time passes, the situation gets worse. So it's almost 1 minute, right? If I'm not mistaken, or 30 seconds. And now you can see more and more formation fluid. I mean, the drilling mud at the higher rate is coming out of the wellbore. meaning that progressively formation fluid is entering the wellbore at an increasing rate. So let's say initially, if the formation fluid was entering at, I'm just throwing a number, 1 gallon per minute. As time passes, it keeps increasing from 1 to 1.1 gallon, 1.2, 1.5, 2. And you can tell by looking at the video that the situation is getting progressively worse. Almost it's 1 or 2 minutes. So already uh, the camera, you cannot see anything because now the camera is also blocked. So I don't want you guys to. So see, now it's fast forward. Um, so it's almost 4 minutes, right? 5 minutes, 4 minutes from the time the kick starts happening. So now formation fluid reaches the surface, and you can hear the voice, the sound of the formation fluid reaching the surface. And apparently is a gas well. And what the only thing we need here is a spark ready to ignite, right? So obviously the entire rig got melted down, and then you see the well is burning. Okay. So I don't want to show the rest of the video. I think this video is pretty self-explanatory, and it tells us about the importance of the well control and why we need to know about well control. And this is the blowout, because if we don't know how to deal with a well control issue, a kick, eventually it will come blowout, and blowout is not desirable at all. And don't one of the reason blowouts happen is when the casing or drilling crew get complacent, because imagine they already drilled, let's say, 200-300 wells in a field, and the field is pretty well developed. They have all the information, all the data, and they think nothing like this could happen. And let me tell you guys this can happen if you don't pay attention. Even in the Permian Basin, which is 2 hours away from us, it's not a high pressure zone. A year or 2 years ago, one of the operators' rig got on fire because of blowout. So it doesn't mean if you are drilling in a low pressure reservoir, blowout cannot happen. Or it only happens when we are drilling through high pressure reservoirs. No, this is a misconception and misunderstanding of the issue. It can always happen. So you have to be always ready, always vigilant about the well control issue. As a matter of fact, in areas that drilling crew don't have any information, they are more cautious, more vigilant, and usually this incidents don't happen. Another important concept on the drilling, on the well control, is mud window. So basically, in order to make sure that never kick happens, never blowout happens, we need to know about mud window, about safe mud weight we can use without creating any issue. As you can see here, there are two lines here, one blue dashed line and one solid red line. The blue dashed line is pore pressure. and the solid dashed line is fracture pressure. Pore pressure can be calculated using seismic data or offset well data, and fracture propagation pressure can be calculated using Hubert and Willis method, or more accurately, Eaton method. Anyhow, when we plot pore pressure and fracture propagation pressure versus TVD, then we define this as mud window. So this area is area number one. Let's call it area number one. And this area, we call it area number two, and this area number three. Let's say out of these three areas we have, which one is the desired one for us during drilling operation. In area one, obviously the pressure is below pore pressure. And when the pressure, downhole pressure or bottom pressure is below from pore pressure, what happens in permeable formations, formation fluid starts entering the wellbore. So if we are in zone one, formation fluid starts entering the wellbore, or we say kick happens. In area number three, where bottom pressure exceeds fracture pressure or fracture propagation pressure, what happens if we are in this area? Lost circulation happens because we end up fracturing the formation. I mean, it's a tensile failure of the wellbore. So loss happens. The only area which neither kick nor loss can possibly happen is area two. So somewhere between pore pressure and fracture propagation pressure. For example, at 10,000 feet TVD, the mud weight or the density of the drilling mud can be somewhere between 11 to 14. So if the mud weight is somewhere between 11 and 14, we can say that in terms of well control, we're drilling safely. If we go below 11, kick happens. If we exceed 14, loss happens. Obviously, as you guys may know, we want to be closer to the pore pressure while drilling than to fracture propagation pressure, because the more we move towards fracture propagation pressure, the more overbalanced the wellbore becomes, and it negatively affects our operation. It increases the cost of the operation because the higher mud weight, the higher overbalance we become. Obviously, the more additives we need to add to drilling mud to make it heavier, and the more additive we add to the drilling mud system, the more expensive the operation becomes, and the more overbalanced we become. On top of that, the more overbalanced we become, the less rate of penetration we get. So we tend to be close to pore pressure, but not too close. Obviously, we don't want to drill right at pore pressure or right at fracture propagation pressure, because if for any reason, let's call it human error, if for any reason we go below pore pressure, above fracture pressure, then kick or loss can happen. To make sure that we're always drilling in the safe region, we need to take into account trip margin, which takes into account the effect of swabbing and surging. And the amount of trip margin varies from one company to another. Let's say 0.1 pounds per gallon is a reasonable number to add and subtract to pore pressure and from fracture propagation pressure. The trip margin is basically uh, is basically for tripping operation. When we are tripping into the wellbore and tripping out of the wellbore, we are changing the bottom hole pressure. How? When we are tripping inside the wellbore, when we are pushing the pipe, what happens? The drilling fluid around the pipe starts moving upward, right? And we know that when it starts moving upward, we always have friction acting on the opposite direction of the flow. Is that correct? So when the drilling fluid moves up, moving upward, friction or pressure drop due to friction is acting downward. So bottom hole pressure will be that amount of pressure, which is equal to the pressure drop due to friction plus hydrostatic pressure of the mud column inside the annulus. So bottom hole pressure is more than static pressure. When the drill string is still inside the wellbore, bottom hole pressure is equal to hydrostatic pressure. When we start tripping in, bottom hole pressure will be hydrostatic pressure plus pressure drop due to friction. Now, on the other hand, when we are tripping out of the wellbore, so what we do, we are removing the pipe. So the level of the drilling mud starts dropping. So the mud inside the annulus goes down. When this happens, uh, friction acts against the movement of the uh, fluid, so it acts upward. So bottom hole pressure would be hydrostatic pressure minus the pressure drop due to friction. So uh, bottom hole pressure will be less than the hydrostatic pressure. For that reason, we need to add trip margin. Obviously, the trip margin we add to the pore pressure is because of swabbing, and the trip margin we subtract from the fracture pressure is due to surge. And obviously, we need to be between these two, the dashed uh, light green line and the dashed purple line. Uh, the the factors which can affect the amount of trip margin, I mentioned maybe reasonable number for trip margin is 0.5 pounds per gallon. However, we need to know what factors can affect uh, trip margin. Uh, the factors can affect trip margin is basically whatever factor can affect pressure drop due to friction. And you guys know that the pressure drop due to friction is a function of rheological property of the fluid. Plastic, we are dealing with bean-can plastic, so it should be plastic viscosity, yield point. It also is also a factor or it's a function of the speed of the fluid. So V, how fast or how slow we trip in or out. And also the cross-sectional area between the drill string and the pipe. So the larger the cross-sectional area, the smaller the velocity of the fluid, and the smaller the cross-sectional area, the higher the velocity of fluid. So these are the factors which basically affect the trip margin. And we need to do the calculation if we want to calculate the actual swabbing or surging pressure. What if we are doing the calculation for floating rigs like drill ship, like semi-submersible drilling rigs, then we need to take into account the riser margin. This leads to another important concept, which is equivalent circulating density, or ECD. Basically, ECD is the downhole pressure divided by 0.052 times TVD. The simplistic definition of ECD is when we're drilling, what is the weight of the mud we're drilling. Let's say if the well is in static condition, meaning that when we start, when the operation has not started yet, so we have the drilling mud, the bottom of pressure is equal to hydrostatic pressure. As soon as we turn on the pumps and we start pumping, the bottom of pressure increases. Why? Because the pressure at the bottom of the well will be equal to the hydrostatic pressure plus the pressure drop due to friction inside the annulus or the annular section. And we know that the pressure drop due to friction is more than zero. So bottom pressure will be more than hydrostatic pressure. So they came up with this concept, equivalent circulating density, saying that, oh, during the ring operation, it's like the well is filled with a heavier mud. I mean, it's not the right term, but this is the concept, the perception of the concept. So for this reason, bottom pressure is not a constant value. Obviously, during operation, bottom pressure is we call it, when we are pumping, we call the bottom pressure dynamic bottom pressure. When we stop pumping and the well in a static condition, we call bottom pressure static bottom pressure. And obviously, dynamic bottom pressure is always greater than dynamic bottom pressure. So, already talked about the trip margin and what factors affect the trip margin. So these are the formulas used to calculate the static and dynamic bottom pressure. For static bottom pressure, 0.052 times mud weight in pounds per gallon times TBD. And in dynamic, it's the hydrostatic pressure plus pressure drop due to friction inside the annulus, and you should be able to calculate that. You need to calculate the flow regime, whether it's turbulent or laminar, and then do the calculate the pressure drop due to friction. If it's laminar, there are certain formulas for that. If it's turbulent, usually the flow regime inside the annulus is laminar, not turbulent, because we don't want to erode the open hole section. On the other hand, the flow regime inside the drill string is almost always turbulent. Okay. For this reason, when we are drilling, for example, a horizontal wellbore, in the lateral section of the horizontal wellbore, the static bottom pressure is the same all the way from the heel to the toe. So when I say heel, here is heel. So at the beginning of the lateral section, we call it heel, and the end of the lateral section, which is the TD, we call it toe. So all the way from here, let's heel, I call it 0.1, and toe, I call it 0.2. So all the way from 0.1 to 0.2, static bottom pressure is the same. So, however, when we start drilling, during drilling operation, these two points don't have same pressure. Obviously, the pressure at 0.2 inside the annulus is larger than the pressure at 0.1. And this is simply because of the pressure drop due to friction, because the mud at 0.2 needs to overcome the friction all the way, all the ladder section, curve section, vertical section to the rig roll, while the mud particle at point one only needs to overcome the pressure drop in the curve section and vertical section. So obviously, the particle at point two must have a higher pressure in order to overcome all the pressure drop due to friction. So uh, now we know about the importance of the wall control. What happens if we fail to manage a kick, and also we know about bottom pressure, the dynamic static bottom pressure. We know about uh, mud window, fracture propagation pressure curve, pore pressure, the safe zone. The next step is why kick happens. What are the causes? There are several reasons, but all of them will be under one umbrella: insufficient bottom pressure. Whenever the bottom pressure goes below formation pressure, kick happens. And as I mentioned previously, bottom pressure is not constant value. When we are not pumping anything, bottom pressure is equal to static bottom pressure, hydrostatic pressure. When we start pumping, bottom pressure is equal to dynamic bottom pressure. When we increase the flow rate, bottom pressure increases. When we decrease the flow rate, bottom pressure decreases. So bottom pressure is not a fixed value. If at any point this pressure goes below formation pressure in a permeable formation, kick happens. So why this can happen? Why bottom pressure goes below formation pressure? There are some reasons here. If one of the reasons, if we pull out the drill string too fast, so we are creating too much of swabbing pressure, so bottom pressure goes below formation pressure. If during tripping out, when we trip out, basically we're removing drilling string out of the wellbore, and the level of the drilling mud drops because we are removing the volume of the drilling string, and we have to replace the volume of the drilling string by drilling mud in order to maintain the bottom pressure or static pressure in this case. If we fail to do that, then bottom pressure drops and it may go below the formation pressure and kick happens. If for any reason formation fluid starts entering the wellbore and basically contaminate the drilling mud and reduce the mud weight. If lost circulation happens, so the level of the drilling mud inside the annulus drops, consequently bottom pressure drops, kick happens. Or if we are drilling and none of these happens, and we start entering an abnormally pressured formations. In general, we we divide all the formations into three different types. The first one is normal pore pressure, meaning that that formation is hydraulically connected to the surface aquifer. Let's say you are drilling in an area close to Gulf of Mexico. As long as the formation is hydraulically connected to the surface aquifer, which is Gulf of Mexico, then your pressure regime is normal pore pressure or normal pressure. If for any reason the formation gets hydraulically disconnected from the surface aquifer, then either we are going to have abnormal pressure or subnormal pressure. So let's go to the next slide. Here you see the three different types of the formations: normal pressure gradient, abnormal pressure gradient, and subnormal pressure gradient. So basically the reason that either abnormal pressure or subnormal pressure formation are found is they are hydraulically disconnected. How this can happen, how a formation can be hydraulically disconnected from aquifer. If we have an impermeable formation, for example, you have sandstone, limestone, all of them porous, permeable. They are connected to the formation, the surface aquifer, and all of a sudden you have a very low permeability formation or impermeable formation like shale, like anhydrite. Then this impermeable formation prevents the lower formations to be hydraulic to get hydraulically connected with the surface aquifer. So those formation will be disconnected, meaning that you will have a pressure trap inside the below permeable formation. And this causes either abnormal or subnormal pressure gradient, depending on the pressure gradient we're reading in those formations. Is it good or bad? During drilling operation, we don't want to see any abnormal pressure formation. Why? Because they are troublesome and they may lead to issues like kick or blowout. However, from a reservoir engineering from the reservoir engineering perspective or production engineering perspective, we want to have abnormal pressure formations. Why? Because reservoirs are basically abnormal pressure uh, formations, right? Hydrocarbon get trapped; it cannot migrate upward because of the cap rock, and we can go and drill and produce. If the cap rock is missing, then the hydrocarbon, the gas or oil keeps moving upward, and it will eventually reach the surface, correct? So uh, abnormal if we are aware of the existence of abnormal pressure formation, then we can take proper actions prior to entering that formation. Let's say, okay, in Gulf of Mexico, normal pore pressure gradient is 0.465 psi per foot, meaning that every foot we drill, pressure increases by 0.465 psi. Let's say you drill 1,000 feet TVD. You expect the pressure increases by 465 psi, right? 1,000 times pressure gradient 0.465. And abnormal pressure gradient, let's say now you're entering a formation with a pressure gradient equals to, let's say, 0.55. So instead of entering at with the bottom of pressure equals to 465 psi, now you're entering a formation with 0.55 psi per foot. So multiply that by the TVD, let's say 1,000. Now the pressure at that area at that point will be 550 psi instead of 465. Imagine your anticipation is bottom pressure should be equal to 465 psi. However, in reality, the bottom pressure is 550 psi. And if this happens, obviously you're going under balance, and formation fluid can simply enter the wellbore and creating kick, causing kick, and then possibly blowout. Does it make sense? So it's very important to basically recognize we see a straight line, which basically tells us about the normal pressure gradient. Here, And this blue dashed line is for West Texas. As you can see, normal pore pressure gradient is 0.433 psi per foot, and the solid red line is 0.465 psi per foot for the Gulf Coast, Gulf of Mexico. If you find any pressure in this area below the normal pressure line, we call it subnormal, meaning that the pressure gradient is less than the normal pressure gradient, which is, let's say, and the Gulf of Mexico is 0.465 psi per foot. Now the pore pressure is 0.41. And if it's above the normal pressure gradient, we call it abnormal. In abnormal pressure gradient, if we don't know about the situation, kick can happen. In the subnormal formation, if we don't know, lost circulation can happen. So let's see in what areas or in what circumstances we can expect to have abnormal pressure formations. The first one is, as I mentioned previously, when we are drilling through a non-permeable formation, because the simple fact that we are drilling through an impermeable formation, meaning that the formations below that impermeable formation are hydraulically disconnected. So there is a possibility to have abnormal pressure formation. Simple. The second scenario is when we expect to go and drill through a thick sand formation. This is the example here. All the way from the surface down to 1,000 feet, we're drilling a normal pressure gradient, and we expect to enter a gas-bearing formation. The thickness of the gas formation is 300 feet, and the gas-water contact is 1,300 feet. The normal pore pressure is 0.465, as you can see here. So if we start entering, and we want to calculate the pressure right at the top of the gas cap, because by knowing the pressure right at the top of the gas cap, we should be able to calculate the required mud weight to enter and drill the gas cap without experiencing any kick. To calculate the pressure at the top of the gas cap, we need to calculate first the pressure at the gas-water contact, and then subtract the hydrostatic pressure of the gas column, so we can find the pressure at the top of the gas cap. The pressure at the gas-water contact can be easily calculated by multiplying the TBD, which is 1,300 feet, by the pressure gradient, which is normal pressure gradient 0.465. So the pressure at the gas-water contact is 605 psig. If the pressure gradient of the gas is 0.05 psi per foot, then the hydrostatic pressure of the gas column should be 0.05 times 300 feet. So this part. So 605 minus 0.05 times 300. The pressure at the top of the gas cap should be equal to 590 psig. Now we know that the pressure is 590 psig. We know the TVD, which is 1,000 feet. So we know the pressure gradient is 0.59 psi per foot. And obviously is more than 0.465. And this is the definition of abnormal pressure formation. To calculate the equivalent mud weight, we need to divide the pressure gradient by 0.052. So the minimum required mud weight is 11.3 pounds per gallon. Obviously, we need to always include safety factor in order to be in the safe side, on the safe side. Uh, so as you guys see, what we how the way we calculated the pressure at the top of the gas cap was first we calculated the pressure in the gas water contact and then subtract the hydrostatic pressure due to the gas column. Someone may ask why we don't simply, we know that all the way from one surface down to 1,000 feet, we are dealing with normal pore pressure gradient. Why don't we simply multiply 1,000 by 0.065 to calculate the pressure, which will be 465? Obviously, the answer is when we have a gas cap, we must have an impermeable layer above the gas cap, which basically disconnects the gas bearing formation hydraulically from the shallower formation. For this reason, we cannot simply multiply 1,000 by normal pore pressure gradient to calculate the gas cap.
Dave and bye.
Sure. Thank you very much. Have a good time. Have a good
Thank you.
rest of your evening or night in Cairo.
Thank you.
Mhm.
Bye.
Bye bye. Bye.